So we thought we could invite you to asking questions, but maybe to encourage some questions, I will start with very short ones on my side. So you see, in 2019, Eric Curiel published a paper in New Astronomy that was titled The Many Definitions of the Black Hole. And he reports a survey that he has amongst, well, a bunch of colleagues working in the field, working in black holes, astronomers, mathematicians, physicists, asking them for the definition of the black hole. And as you can imagine, he got many answers, usually completely different, maybe complementary at the end. And needless to say, also identifying the particular field the respondents were coming from. And just to help you, there are some notions coming from different fields that people used in, or could use in defining black holes. So for instance, in astrophysics, you talk about compact objects, regions of no escape, engines of enormous power output. In classical relativity, there is a classical definition of causal boundary of the past or future null infinity. That is something which is known as the event horizon, or the apparent horizon, the quasi-local horizons. In mathematical relativity, people talk about apparent horizon singularities. In quantum gravity, for instance, they say they think about particular excitation of a quantum field or an ensemble or mixed state of maximal entropy, etc. Right? Mm-hmm. So, which answer would you choose?
They all seem quite good to me. So the classic like definition of a black hole, which was we talk about in the book actually, was thanks to Roger Penrose, so the idea of trapped surfaces. So the idea that it's a region of space-time in which there are rays that end. The idea of that there are regions in space-time where rays of light stop. So the idea of the end of time in some. So I like that one. But the idea of the key aspects that matter for the stuff I've been talking about, I suppose, the idea of the event horizon of the black hole and the idea that there is very strong gravity at the center. So I mean, the idea that at least in classical general relativity, there are singularities hidden by horizons. So singularities hidden by horizons is probably what I would go with.
Mm-hmm. So very classical.
Yeah.
I was thinking about quantum things, given the lecture, but...
yeah.
Good. Okay, so the next one is as follows. So as you mentioned during the lecture, the concept of the black hole originated within classical general relativity. And about classical general relativity, we can say that it has some experimental evidence. And this ranges from, of course, having Newtonian gravity as a limit, which is very well confirmed, but also you can say that the technology that allows us to have GPS or our navigation in cars, it's based on GR calculation. It wouldn't work without gravitational corrections. And finally, we have things like detection of gravitational waves, which are, of course, also a clear experimental evidence. Now, when it comes to quantum aspects, unfortunately, we cannot say so. Right? It's basically right now there is no observation whatsoever, and we construct our understanding by fitting different puzzles and what we know about quantum mechanics.
Yeah.
But if you were hoping for some chance of experiments or observations, what would be the direction?
Yeah, so this obviously is a very, very important question. Otherwise, what I've been talking about is borderline like metaphysics, or it's not physics unless we can do experiments that confirm or refute I mean, maybe this is a bit old-fashioned of me, but I believe that's the case, right? That we learn about the world, right? And it is the case that, and this is one of the wonderful things that being a physicist, being trained as a physicist, the things that I really appreciate is that it's a humbling experience in that it teaches us how easy it is to be wrong and to fool ourselves into thinking that we understand something when we don't. Right? So with that warning in mind, the question that you're asking becomes, it's an acute question, like maybe this is not correct, right? How do we prove that it's correct? Right? And we're going to prove it by doing some experiments. Now, black holes, we saw from the talk that what happened is that the interest morphed into understanding if I can understand that there is a geometrical nature, a gravitational, so using equations like the equations of gravity to describe quantum systems in this holographic way. That's the big idea that's at stake, right? Is it the case that space is built out of entangled quantum units, right? Well, we have the possibility of doing experiments where we entangle things like that error-correcting code and look to see, and making measurements on the system to see if we can equivalently describe that system using equations which resemble Einstein's general theory of relativity. So classical gravity equations to describe quantum entangled system. Is that possible? That would be, for me, I mean, that would be one of the greatest discoveries, I think, in my lifetime, if that would be found to be the case. And it's only now that the experiments, so the developments in experimental physics over the last 30 years or so, developments in low-temperature physics, in laser physics, which have led to the ability to control small quantum systems to such an extent that you might be able to build things like this. This is the precursor to building a quantum computer. You've got to be able to control with wonderful detail single atoms, right? That's only just recently been happening, exploiting that to do experiments that could confirm the ideas that I was talking about at the end of the talk. I think that's that's where the experiments are.
So you would hope for some kind of analogous or analog experiment.
It's an analog, but it's an analog in the sense of being completely,
of course,
like it would be strongly suggestive that that this is the way in which our space is constructed. It would be quite remarkable to make the call and say, I think if you do this, you get something that looks like gravity. You do it, it looks like gravity, and then to say, but our space, for me, that would be convincing.
Okay.
Yeah.
Okay. So maybe some questions from the audience. And by the way, you can either ask in English or you can ask in Polish, and then we can try to translate. So, yes, please.
Okay, I have two silly questions, but they are really silly. If I remember correctly, you mentioned that at the horizon the temperature rises to the infinity. And what does that mean, considering that the temperature is the measure of a mean kinetic energy? And the second one, during spaghettification, okay, maybe I don't understand that concept, but the whole space-time is spaghettified, right? So is the metric changed in the space-time? So for the spaghettified object, nothing should change, right? Because the metric is changed.
Yeah, yeah.
To be
but neither of those was a silly question. Yeah,
exactly.
So I'll deal with the second one first. So the metric doesn't change. So the metric is, as you say, it's just a representation. So you might be tempted to think that the space-time is static, then, that the space doesn't change, so how can it spaghettify? But from what actually effectively happens is that when we write down coordinates, global coordinates to describe the black hole, right, what we think of as time and space swap round in the interior. So what the journey to the inexorable journey to the singularity is what we would have thought of as was an inevitable journey into the future.
It's because we are spaghettified in time, not in space.
No, no, no. There is from the point of view of somebody inside the horizon of a Schwarzschild black hole, right? With if you know about the I think you may know, like imagine the Kruskal picture of a wormhole, right? So that describes the process of the inability to reach as we fall into the singularity. What is happening is the space is becoming stretched out. So space is, from the point of view of somebody inside the horizon, space is dynamic from the point of view of a local observer inside the horizon of the black hole. So making statements like the space is static is a global statement, right, which is not something, that's kind of something that's a characteristic of coordinates. It's not a feature of what actually happens. If you jump inside of a black hole, right, it will be as if, say, the atoms on your head and the atoms on your feet, it's as if it would be like a rubber sheet and the rubber sheet is being pulled apart. So your head gets further from your feet. That's what actually would happen to you, right? But so it's okay. I've said it. I'm risking saying it more than once. The other question was, just remind me what the other question was. Oh, about the infinite temperature on the horizon. Yeah. So that is only the case. So remember that I said if you just fall through the horizon freely, there is no temperature. There is nothing special about the horizon at all. Then. So it's not an absolute statement, from the point of view of somebody hovering close to the horizon, right? With a thermometer, the thermometer reads a temperature, and that temperature goes up and up and up, the closer and closer and closer we get to the horizon, right? In the limit, right? So this is a little bit of quantum physics associated. It's not much quantum physics, right? This is an effect which is basically very closely related to an effect very close to the horizon of a large enough black hole, an effect called the Unruh effect. We move very close to the horizon of the black hole. It's like it's an infinite temperature membrane, but presumably what's actually happening is that, as you say, it can't go to infinite temperature. Something must happen, right? So this would be within a very, a tiny, as we approach the horizon, we just lose our ability to actually work out precisely what is happening at that point. That process is presumably related to the process, but how the book, when I throw the book in, it gets burnt up and then comes out. That is, that last little bit is, we need to understand that in order to properly understand, and nobody understands that at the moment. So that requires more quantum physics than we've got. The quantum understanding that we do have has got this idea that the temperature just rises up to infinity at the horizon, but that can't be the case. There must be a point where the description needs to be improved. Is that okay? Yeah. Okay, yes, please here.
I would like to ask you about this picture you talk about. I'm afraid I don't understand. You mean explaining this is the error propagation code of entangled particles create geometry of space?
Yeah, let me, I did go through this quite quickly. Let's imagine that we know the state of all these qubits on the boundary, right? Then the rule is, and I just referred generically to this as error correcting and spoke in broad terms, but I can give you a little bit more detail. So if you see that there are 5 lines coming out of this, right? If I know 3 of them, I know the other 2, and I know the red one, right? So in this case, if I know this one, and this one, then I also know this one, and this line going into this one, right? That's good, but I've only know 1 line going into this one at the moment. But if I know these ones, I can know this line. And if I know these ones, I can know this line, which means I know this one, right? And in that way, I can, with a little bit of thought, you can kind of, using the rule that if you know any 3, you know the other 2, or you know the other 2 plus the red one, you can then ask, if I only know this, how far inside do I get? How many of the red dots do I actually know if I know these ones? And the answer, in fact, if I draw it, look at that line there. Can you see that line that I'm tracing out with that line is a geometric line on the Poincaré disk, right? If I know all the qubits, if I took these qubits off down right onto the boundary, you know, I can't draw it. The pentagons get really small down here. But if I did it and I knew all the qubits on the boundary from there to there, the amount by which they are entangled quantum mechanically, there's a way we can calculate that, with all the other qubits, that the amount of entanglement is proportional to that distance. So the quantum entanglement is telling us what the geometry of the Poincaré disk is. That's that's what's going on. Yeah.
Thank you.
I have two questions. I would like to know your opinion about this theory, this new theory by Durham University and Space Institute of Barcelona that removes a singularity and says that instead of singularity, there is a kind of stable region, very, very curved in the center of the black holes. And the second question is also connected to it. One of the researchers, one of the scientists connected to this theory, says that the final effect of the evaporation of the black hole via Hawking's radiation might be the micro black hole, and that these micro black holes could be a good candidate for the dark matter.
Okay, I don't know enough about that to answer that question. I can say that on the first point about the absence of a singularity, I think generally that it's expected that the complete description, see the complete description of a black hole in particular when we think of throwing something in and then that thing coming back out again in the Hawking radiation when the hole disappears, then we need a description of that from the point of view of the thing that got thrown in. Remember, the thing that got spaghettified. And the spaghettification process leads to a singularity, which is that the thing stops existing. Well, that can't be what happens if the stuff comes back out again. It can't stop existing if it's outside, right? So the idea that when we get to the point close to the singularity, which is this infinite stretching of space, that some more, that we're not there. We don't understand that physics sufficiently well. You know, that's the goal would be to work out how the information gets back out of the black hole, right? When it travels into the, but not, you know, it would be likely that would not involve any singularities at all. Singularities are in the place of infinite density. They're more a signal that we don't understand the physics than they are of you know, anything that, you know, that they exist in nature. So I don't know about the research that talks about the geometry, you know, make some statement about what the geometry actually might be. It sounded like the idea that the information that was thrown in, an old idea that it kind of gets, the black hole doesn't completely evaporate and it stays like a little nugget at the end. Doesn't completely disappear, and the information is inside the little nugget. That was disproved in a series of like papers relatively early on. So I wouldn't, you know, or at least not disproved, but shown to be extremely difficult to construct models in which black holes, like you can see that if a black hole doesn't totally evaporate, but just evaporates to a very small thing, that you can still have all the information in the little small thing, and it doesn't have to come out in the radiation then. It's where's the information gone? It's gone into the little thing. That would be a resolution to the information paradox, that the information is just locked away inside these little nuggets. That's different from what I've been talking about. I don't know if that connection is what was being talked about then. And I'm sorry, I don't know that paper.
Okay.
I think there was a question before over there. Yes. Yes, I think, Professor 𝗝𝗲𝗳𝗄, yes.
I would like to take your picture, holographic picture, at face value. And of course, I don't know to what extent ADS-CFT theory does it formally. But if you have, of course, with the help of holographic picture, I can understand that you can map the three-dimensional interior of the black hole via two-dimensional, some sort of holographic picture at the surface. So, but then, in order to have a coherent holographic picture at the surface, you need a coherent radiation inside. Does that mean that there is some sort of in-phase particles which condense, which can propose this holographic picture? Because you said that the black hole is composed of jiggly things. Which are those?
Well, space is.
Space,
yeah.
space. Oh, space. Okay, but black hole is also essentially closed space. So therefore, is it like that those because you have photons essentially inside the black holes, and you have this beautiful holographic picture resulting at the surface. Therefore, the black hole can evaporate via Hawking radiation or something else. Or are they actually in the black hole the material atoms which form some sort of this coherent picture which produces this holographic picture? Maybe this is very naive or even physically wrong picture, but I would like to know what is the real connection between this three-dimensional world inside and this two-dimensional holographic picture at the surface.
I'm not sure. Do you understand the question, really? Like,
well, vaguely, but...
How do you relate three-dimensional solution to this holographic picture of the
everything is taking place in our world. So maybe that like, it's not like this is a virtual description, right? So maybe this helps, I don't know. But some recent papers have, in particular by Jeffrey Pennington in Berkeley, have asked the question, see, imagine I get this region of space here, and I imagine I could cut it out. I could like cut out of this, the space. So I've got a ball of empty space, right? Obviously you can't do that, because we can't do that. But would it be the case that the interior of the ball would be encoded on, in some sense, on the entanglement structure, like the way in which we're talking about the properties of empty space here, so the properties of what we would call the vacuum, right? So the entanglement structure of the vacuum. Is it that that's holographic? That any region of space, so when I talked about the content of a library being basically encoded on the boundary of the library, I was being, in a sense, serious now. So it wasn't just an analogy. So basically every region of space, due to the fact that there is this entanglement structure of the vacuum, is encoding this information, and the only reason that we've found it first in the context of a black hole is because we kind of can cut the region of space out in a black hole. The horizon is like doing that job for us. There's an infinite amount of time dilation on the surface of the horizon. That's allowing vacuum fluctuations to start to become like, accessible. So it's like we've spotted this, right? They become real in the case of the Hawking radiation. So black holes are the first glimpse, but likely, and certainly it is the direction of travel of the research, is that we just discovered this holographic idea there, and it's more general.
Okay, it's completely different with what I meant from the condensed matter point of view. But anyway, thank you.
This is condensed matter-like, though. So this would be like calculating the entanglement entropy of some network, right? And the fact that there's an area law in the entanglement entropy in condensed matter physics, that's closely related to this. So the idea that there might be a local entanglement structure, and if you calculate the entanglement of some region with the boundary, the entanglement is proportional to the area of the boundary. That's like a result due to like John Cardy and people some time ago in condensed matter physics. This is very closely related to that.
Okay, thank you.
Okay, thank you. Yes, maybe a question over there. Yes.
Okay, thank you. So I would like to ask about this thermodynamics analogies, about the second law, actually. So what is the physical meaning of this increase of the area of the horizon and as an analogy of the entropy increase in the context of black holes?
Yeah, when we throw something into a black hole, right, that information is gone, right? We lose access to that information, right? Which means that the entropy of the black hole must increase, right? And the entropy is, so that, right? So it means the area of, well, the entropy of the black hole increases because we've lost the information of the thing we've thrown in. But if the entropy is the area increases, right? So if your question is, how does that, we don't know. I mean, that connection between entropy, you know, how it is that the information is getting ripped to pieces. I mean, it looks like what happens is the information gets completely, maximally, so whatever I throw in, right, all that matters is its mass, basically. The black hole will rip it to pieces and spread it across the horizon of the black hole. That looks like what happens, and cause the black hole to grow a little bit. So you throw things in, it gets utterly obliterated, shredded up in the maximum way it could be, and then tiled, a bit like all those zeros and ones on the surface of the black hole. I mean, that was just to represent that that's where the information goes. And it seems to happen very quickly, that. It seems to, so the idea, so trying to understand how the dynamics of that process it's not understood. It's related to the question that was asked before about as the temperature goes to infinity, we don't know what's going on. But we do know that it appears that black holes are very efficient at scrambling the information that gets thrown into them. Yeah, but the way in which that happens, you know, if you like, you're trying to encode the information on the whole onto the horizon. You've got more information there. You need a bigger horizon to encode. So the horizon is kind of. Right. That's certainly the case if the information is being encoded in small units of like basically a fixed size, which is what it looks like. It looks like they're Planck size, if you know anything about. Basically, there's a kind of very small distance in physics, and it looks like the information is being encoded in units that big on the horizon of the black hole. So, yeah.
Any more questions? Maybe yes, there was one over there.
Hello. So the black holes are one of the solutions of Einstein's general relativity that appear in nature. So, but there could be some symmetrical solutions which are referred to as a white hole, and I would like to ask if the physicists could potentially relate somehow these white holes to the point zero of the Big Bang, because the black holes are the objects which are which have the attractive forces, while the white holes are the hypothetical objects which have the repulsive force. So, do you see some perhaps connection between the point zero of Big Bang and the white hole?
Well, I can see the connection. I'm not aware of. I mean, Stephen Hawking was very interested in, like, the mirror of the singularity inside of a black hole, like the converse, the singularity at the start of the universe. But it wasn't as simple as though, like, kind of the white hole solution that one finds in solving Einstein's equations. So the white hole and the black hole do come together as pure, so not in the environment of a collapsing star or anything like that. You can write down solutions to Einstein's equations, but it's got both in, which is what you're referring to. But the white holes in that scenario aren't, as far as I'm aware, you know, they're not related to a viable cosmological model of the universe. So okay. I'm not aware that. I mean, I don't know. It maybe
it's kind of. The question is between the physics and metaphysics, I would say, no?
Well, I mean, what you would, it's a physics question in that but it would be incumbent upon you to write down some kind of model, of cosmological model, which could represent the kind of universe that we live in, right? And I'm not aware of any cosmological model built in that way.
Okay, thank you.
Yeah.
I would like to know your opinion. I have such question. Do you believe that in one point of our life we will get all essential ingredients to decode our reality, and what will be the result of it? For example, we know how our reality is encoded. Does it mean that our world will collapse because we know everything, and so we can interfere the reality, we can like change it? So, like, this metaphysical question. Like,
yeah. Well, I tend to think so. I tend to think that what we know represents a tiny fraction of all there is to know. So basically, we're just scratching the surface in our understanding of the cosmos. So that kind of, I see no evidence that we're approaching some kind of grand theory of perfect knowledge. Or, I mean, I can't even calculate what breakfast cereal I will eat in the morning. So we understand very little, really. Understanding that space is not what we think it is quite different from a profound, from like a knowledge of everything, right? It's just a knowledge of one thing. There are very complicated problems in the world, like, and the most difficult ones are the ones related, like predicting what the weather will be tomorrow. Those are immensely difficult problems. Working out what happens when a bunch of 50 or 100 molecules are in the vicinity of each other. We can't do any of that at the moment, really. So this kind of highfalutin physics is dealing with, it's very narrow in its scope, right? It's focused on particular, I mean, admittedly, like profound questions. Really, this is why I like why I do it. But to emphasize why I think what I think, right, is I talked about the quantum computer, and I said that a 300-qubit quantum computer, just to represent its state, to say what, like, at any given moment in time, would require a classical computer that is using every atom in the entire observable universe. So in other words, it's impossible. Right? Processing information in the context of that kind of object, a quantum computer, we've not even begun to understand how that works. Nobody, no human has got any intuition on that. This idea that maybe this quantum entanglement, which is what we're talking about when we talk about this quantum computing thing, it's this feature, that it may have an important role in explaining how space is constructed, right? That's the beginnings of an understanding of what entanglement is, right? Nobody's ever done, it's like we are little children who've never done a calculation in this is called Hilbert space. It's real quantum physics, and we've never really done any real quantum physics. It's been around 100 years, quantum physics. We've built semiconductor chips. Technologically, it's changed the world, but we've always been focused on like one or two particles doing one. We've never really come to terms with or understand the power of quantum physics in describing systems with lots of particles in. So that's the sense in which I'm saying we have definitely only just scratched the surface there. This also relates to the condensed matter physics, because like understanding these systems is, this is what is going to be a big part of modern physics over the next 20, 30 years, because we know nothing and we're going to learn some more.
But if we are part of this system, is it possible to understand it at all? Like, if we...
I mean, I mean, yes, demonstrably, right? There's a kind of pithy answer. I mean, like, we do understand a lot about the world. But the idea that observations can play a fundamental role in changing the nature of the way things are, that is a feature of quantum mechanics. But one that, it is a feature. there's a great quote from John Wheeler that basically this is a participatory universe, right? Which is kind of reflecting that idea that the way we shape the universe is determined by the things that we choose to measure, right?
Mm-hmm.
Yeah.
Thank you.
So unfortunately we are under some time limit, but let's say we can afford 2 more questions. So I saw the question over there. Right?
Ja zadam pytanie po polsku. Sorry, bardzo bym prosił o przetłumaczenie. Z tego, co zrozumiałem, jeżeli chodzi o wykład, mówi Pan o informacji, która dochodzi do horyzontu zdarzeń. Proszę o przetłumaczenie.
As far as I understood your lecture, you were speaking about the information that reaches the event horizon.
I w momencie, kiedy ta informacja dochodzi, ja rozumiem, że na horyzoncie zdarzeń taka pojedyncza informacja tak jakby sama z sobą interferowała i w tym momencie, tak jak w eksperymencie szczelin podwójnej szczeliny, jeżeli ta informacja interferuje sama z sobą, to wówczas jedna część, czy mogłaby ta jedna część w postaci promieniowania Hawkinga wypromieniowywać, a czy ta druga część mogłaby wówczas być tą informacją, która wpadałaby, tak jak Pan powiedział, nie ginie w tej czarnej dziurze, więc wpada do osobliwości. I jeszcze biorąc pod uwagę, że...
Well, let me go with the translation, especially that it's sort of difficult.
I got the end of that. But
okay, so the question was that you could think about some analogy between the standard double-slit interference and the information reaching the horizon. So I understand you are thinking that that you could somehow understand that information interferes, and then we could think about the portion of information that drops into the black hole and the portion of information that is radiated away in the form of Hawking radiation. Now, of course, well...
Yeah, the idea, so I don't know how to, but there is a particularly interesting thing that happens near the horizon of a black hole. So the Hawking particle that comes out is associated with a partner particle that it's entangled with that falls into the singularity. So that's the mechanism of Hawking radiation, right? Now, the particle that comes out, ultimately, when the black hole has evaporated, this particle is still traveling. If the black hole has evaporated, the information associated with the particle that went in needs to come back out as well. So there's going to be, in some sense, radiation at some other time emitted, which contains the information of the guy that fell in. So the radiation that is out has got to be entangled. These two photons, particles of light that come out, need to be entangled with each other, so to say. But the photon, one of the photons is entangled, or was entangled, with the one that went in as well. Right. Now, there's a principle in quantum physics that says that one particle can't be entangled to two particles at the same time. So it's called a monogamy of entanglement. So we've got a bit of a problem now in that we kind of want one particle to be entangled with two in order to explain the information paradox. And this, for a while, created a big problem, which led to what was called the firewall paradox. Right. And the idea now, this is just, I guess, to illustrate just how crazy like the thinking is, or at least how counterintuitive it is, right, is that the photon that's inside is the photon that's outside, right? There is a sense in which they're the same, right? And it's not a copy of it, so because that's also not allowed in quantum mechanics. So the asking questions about what happens to the infalling modes, the infalling particles that are produced when Hawking pairs are produced, and how that is related to the information that comes back out again, that is actually a topic of contemporary research. And it is also, the people who are making most progress on that are people actually who are also like tackling problems in quantum information theory. So it's yeah, because you consider this is very kind of
I would like to refer to the moment when you explained the holographic principle. As far as I understood, you said that if you have a quantum theory on a ring, it encodes everything which is inside of the ring, and then the gravity is an emergent effect of this encoding.
Yes.
So in this sense, the quantum theory is somehow more basic than gravity. So you get the gravity from the quantum theory. Do you know anything about the approaches that try to show that you can get a quantum theory from the relativity, or the ST?
It's a good, so certainly the way that I've presented things, and that picture there, which is quantum mechanics all the way. So this is quantum mechanics, and here is a way of arranging a bunch of quantum objects, quantum bits, in such a way that we get an emergent gravity theory. That's certainly suggestive of the fact that the quantum theory is more fundamental. And in fact, it's taken literally, this kind of thing says that if I know the quantum mechanics on the boundary, that is the quantum theory of gravity. So that gives me the full theory of quantum gravity, not just classical gravity. So that, like general relativity, it gives me all the quantum corrections to it as well. So I get a complete quantum gravity theory from this line of thinking. And then quantum mechanics is fundamental. But people, I would hesitate to say that there's no sense in which that's proven that that's the case, because it's very hard to calculate in these systems to actually demonstrate that you've properly understood, you know, but that is going from the other direction, starting with gravity. Right? Classical gravity does only ever emerge in these holographic theories as in some approximation of the boundary theory. So in that sense, you can't get the whole boundary theory just from the classical gravity theory.
Okay. So I think it's already 8. And I think it's time to stop. So one good news is that we have a surprise for those who are actively asking questions. Namely, there are some books by today's speaker, which can be distributed as a gift for those who are asking questions. So maybe it's possible to collect them after the lecture. And now I would like that we all ask the speaker once again, and for the talk and for the discussion and all the answers. Thank you very much.
Thank you. Thank you very much.
And of course, thank you very much, all of you, for coming and joining us today.
So if you could stay just for a second. So I know Jeff since 25 years, and I haven't seen him for quite a long time, and it was really exceptionally nice to see you here. I thank you for your enthusiasm, for your inspiration, and for the intellectual adventure. So let me offer you a very little gift from our faculty. So this is a pen with coat of arms of our university. And this is, I hope that you may input some new information in your new book with this pen. So thank you, Jeff.
Thank you, Leszek. Thank you so much. Yeah, that's really good. Thank you.